just like this were made by Carl Benz in the 1880s. They were made of metals of different kinds. There was wood, rubber, canvas, but no plastic. In those days, plastics as we know them didn't exist. Today, it's a different story. More and more car parts are being made out of plastics. Why have plastics been chosen for so many of these parts? Do they do the job better, or cheaper, or are other materials no longer available? To answer these questions, we need to find out more about plastics. Plastics are synthetic materials. That is, they don't occur naturally. They're made in chemical factories from crude oil or natural gas, extracted by drilling underground or beneath the seabed. Crude oil contains many different chemicals. In an oil refinery, these are separated by heating the oil. Some of the components are used to produce petrol. Others become the building blocks to make plastics in specialized production facilities. These building blocks are molecules called hydrocarbons because they contain hydrogen and carbon atoms. They're also called monomers, small units that in the right conditions react together to form long chain molecules, like a string of beads, called polymers. So a piece of plastic is a mass of these long molecules. Different kinds of monomers can be produced from oil. This means that many different plastics can be produced, with different melting points, densities, and other properties. These are all synthetic materials. In other words, they don't exist in nature. The polymer material is usually cut into pellets for easy handling and transport. The production of plastic materials from raw materials is primary processing. Plastics can be divided into two main groups: thermoplastics and thermosets. Thermoplastics soften, then melt when they're heated. As the plastic cools, it hardens in whatever new shape it's been given. This is one of the properties that make plastics so useful. Thermoset plastics, like melamine, form in a different way. When you heat a thermoset, it doesn't melt. Instead, the heat causes the material to break down. This change can't be reversed, so thermosets can't be recycled. Thermosets play an important part in composite materials, and we'll look at them in a separate program. In this program, we'll concentrate on thermoplastics. From different building blocks, many familiar thermoplastics can be produced. A plastic like polyethylene can even have different grades with different properties. Here's two pieces of polyethylene, same size, but the left one is low density, the other is high density. They're made from the same building blocks, but the size of the polymer chains and the amount of branching in the chains have been varied by changing reaction conditions like temperature and pressure. LD polyethylene is useful for products that need to bend easily. HD polyethylene is used where greater strength and rigidity is required. Like metals, plastics can be mixed together to make alloys. This radiator grille is a plastic alloy called ABS. It's made from three monomer building blocks. Acrylonitrile, which provides chemical resistance. Butadiene gives it toughness and impact strength. And styrene provides rigidity and makes the material flow better in the production process. With so many building blocks and different possible ways of combining them, you can see why there's an enormous range of plastics. They're designer materials. Their properties can be varied and precisely controlled. This product, rope made from polypropylene, actually lists some of its properties. Some of these, like resistance to acid, are chemical properties. Others, like strength factor and floats, are physical properties. Let's first look at some of the important physical properties of plastics and how we measure them. Any material has many different properties. Physical properties include tensile strength, the ability of the material to resist being pulled apart. Tensile strength can be measured in a tensometer. Test pieces are clamped and then stretched. This piece is a type of polystyrene. The aim is to measure how much the material stretches as the force is increased. And the force that causes it to break. Polypropylene has better tensile strength. The same stretching force doesn't break this sample. Tensile strength is obviously an important factor when choosing materials to make rope. Nylon has even higher tensile strength. This gives it many uses, including fishing lines and instrument strings. Here, nylon's elasticity helps to soften the jarring on the climber as she descends on the rope. Impact strength, or toughness, is the resistance to fracture by impact. Here's one way of measuring it. The IZOD impact test. A sample with a notch cut into it is struck with a weight. The sample here is high-impact polystyrene. The instrument measures how much energy was absorbed by the material before it broke. Xenoi is a blend of polycarbonate and PBT, a close relation of PET. Let's see how it handles the same impact. It absorbed more of the energy before it broke apart. This higher impact strength is one reason Xenoi is used in cars for fuse boxes and other protective housings. Polypropylene has good impact resistance, and it's often used for bumper bars. Ice cream tubs are also made from polypropylene. It keeps its high impact properties at low temperatures. The lids are sometimes made from low-density polyethylene. They need to be flexible, and impact strength is not so important. High-density polyethylene is used for high-impact situations. In this case, repeated punishment has pushed the material beyond its limit. Brittle materials have low impact strength. Polystyrene, used for CD boxes because it's cheap, transparent, and has a very high sheen, has low impact strength. Stiffness or rigidity is another important physical property. This is the resistance to bending or deflection. Here, we're measuring the deflection of samples with the same size and shape when we subject them to the same load. From the front, we have low-density polyethylene, high-density polyethylene, nylon, polypropylene, and Xenoi. Of these sample plastics, low-density polyethylene shows the most deflection. Xenoi shows the least deflection. In other words, it shows the most stiffness. PVC pipe is extremely rigid. Many products are made from a more flexible form of PVC. In this case, the material is made more elastic, adding plasticizers, particles that keep the PVC molecules apart. The material can change shape, but return to the original position when the force is removed. Over time, UV light breaks up the plasticizing particles and they evaporate away. This makes the PVC material more brittle, and cracks eventually develop. Hardness is the resistance to scratching and indentation. One way to measure hardness is to drop a weight, like a plumb bob, onto a test piece from a standard height. The harder the material, the smaller the indentation. Here are the results for 4 different plastics. Friction is another physical property that's important in some products. Nylon is now widely used for gears. It's hard wearing, and the low friction surface means very quiet running. Thermal or heat properties are about how the material behaves at different temperatures. We'll heat acrylic, which is quite rigid at room temperature. We can now bend this material into a completely new shape. If you change your mind, just put it back in the oven. The acrylic returns to its earlier shape. Now you can try again. Thermoplastics generally have much lower melting points than metals, and this makes them much easier to form into useful shapes. There is a downside. This vinyl record was left in a car on a hot summer's day. Different plastics soften and melt at different temperatures. Low-density polyethylene on the left melts at around 80 degrees Celsius. Nylon on the right will not melt until 250 degrees Celsius. The relatively high melting point of nylon makes it suitable for many cooking utensils. Allowance sometimes has to be made for the fact that plastics expand as they heat up. The gap here is to allow for expansion on a very hot day. Without the gap, the surface could buckle. This equipment measures another important property of plastics known as melt flow, how easily the material flows when it's melted. You might think this would be the same with all plastics, but it isn't. The bigger the molecules in the plastic, the harder it needs to be pushed to make it flow. If the material doesn't move fast enough, there's a danger that it won't fill the mold properly, especially if there's lots of small spaces to fill. Plastics are generally poor conductors of electricity. This makes them extremely useful as insulators around anything that carries electrical current. What are chemical properties? Here's an example. Water has started to rust the steel in this bumper bar. A chemical change is going on to form a new substance. So one of the chemical properties of steel is that it reacts with water. Plastics don't react like this with water. They resist corrosion. This is one of their chemical properties. But plastics can be affected by other substances. Let's add mineral turpentine, TURPS, to a polystyrene cup. Notice that the bottle is also a plastic, PET. The chemical properties of these two plastics are clearly not the same. PVC can be dissolved by a solvent such as acetone. In this way, PVC pipes can be glued together, making them useful for plumbing. Polypropylene can't be glued, so it's rarely used in plumbing. For petrol containers, you can use polyethylene, but it has to be a very high-density polyethylene. Many plastics are affected by ultraviolet radiation. This is the result of exposure of a polyethylene sheet to sunlight for a number of years. The same with this garden fork handle. Paintability is another chemical property. When polypropylene was first used for bumper bars, they had to be left unpainted because paint wouldn't bond to the surface. Now, flame treatment is used to change the surface chemically so that polypropylene can be painted or chrome coated. So, plastics have many properties: physical, thermal, electrical, and chemical. They guide your choice of the right material for the right job.